Please come back to the hall. Okay, it's time to start with the afternoon session. This session is called Number Theory in Cryptography and is chaired by Professor Carlo Blundo. Professor Carlo Blundo is professor in University of Salerno, which is in South Italy, and is also the scientific director of the componenti CIFRIS. Carlo?
Okay. It's an honor to introduce you Professor Antoine Joux. Currently, he is with permanent researcher of the Helmholtz Center for Informatic Security in Saarbrücken, and he also an honorary professor at Saarbrücken University. Formerly, he was with the University of Versailles, and he was chair of cryptography at the Sorbonne University Foundation. His research area is, of course, cryptography, with particular focus on cryptanalysis. And for his research, he received several awards. Just to cite a few, in 2013, he's the winner of the Gödel Prize for his work on multi-party Diffie-Hellman key exchange. Next year, he was nominated fellow of the International Association for Cryptologic Research. And later, in 2019, he was a recipient of the EACR Test of Time Award. His talk will be on about identification protocols and signature schemes for group action using the multi-party computation in the Hell paradigm. And the stage is yours, Antoine.
Yeah. So thank you, Carlo. I hope you hear me well. So first of all, I would like to thank the organizer for inviting me here. And okay, so sorry for not being formally dressed. I didn't know it would be such a big event, but I hope you will bear with me. Okay, I thought I would have some pointer, but I don't. So okay, I will try to indicate what I am pointing at in a reasonable way. Okay, so today I want to speak about multi-party computation in the head because it's something that is really interesting and that has been seen a lot recently to create a signature scheme for post-quantum crypto. But I find that it's a little bit difficult to understand in all generality. So it's quite nice, I think, to be able to look at easier example and figure out how it works on specific cases where most of the technicalities can be smoothed out and become easier to understand. And that's what I want to do today. And I will show you how to do multi-party computation in the head and go to signature from isomorphism and or group action, because these two things are basically the same thing. Okay, so first, what is multi-party computation in the head, and when did it appear? So it's something that that was introduced by these people, Ishai, Kushilevitz, Ostrovsky, and Tsai. And basically, what they had in mind at the time when they introduced this, so it was 2017 or 2016, I don't remember the exact date, but it's quite recent. And what they had in mind was to propose something to make asymptotic scheme using very strong asymptotic scheme using multi-party computation. And it was kind of a theoretical idea at the time, but let's go through it. So what you have is a very generic tool. Assume that you have an NP relation, so you have a relation that relates some value x, which is a kind of a statement of a problem, together with a witness that you know a solution. And you can check this, once you know the solution, easily in polynomial time. So now if you can check it concretely, you can also design a multi-party protocol that will check it, not with a direct copy of the witness, but with a shared copy between all the parties. And that's precisely what they do. They create a multi-party protocol that, given as input a sharing of W of the witness and the value X, just compute the value of the function using a multi-party protocol that doesn't leak the secret to the participant, as long as they are not all of them contributing or not a big fraction of them contributing. Okay, so this is the starting point. And what is multi-party computation in the end? The idea is that now you have a prover and a verifier, and you want to do, let's say, zero-knowledge identification. And the prover is going to take this multi-party computation, and is just going to run it, what we call in its head, by emulating, like if we were running on a virtual machine. So he opens one virtual machine for every party in the computation, and then he lets them run the protocol that checks that the witness is correctly shared. Okay, so at first he shares the secret that he knows because he is the prover. Then he runs this protocol using virtual machine, and once he has done this, he looks inside every machine. What is your history? What have you done? What have you seen? What message? What have you done? And he just commit to what is called the view of what the people have done and the computations they have done, etc. But not. And after doing that, he just commit to this view. So committing is a pretty standard thing in crypto. Basically, you just take all the things together, you hash them, and nobody is able to reconstruct a credible history that will have the same hash, because that would imply doing a collision. So it's cool. And after that, the verifier says, okay, I want to check that you are not doing something weird. I want to check that what you have done in your head is indeed honest. So in order to do that, I take your commitment to what you have done, and I randomly ask for a few parties, or maybe all but one. That's what we will do later on. But you ask for some party, and you want to check what they have done. And in order to check what they have done, you just describe the full view of what they have done and what they have seen. And once you have the full view, you can check that the protocol viewed by this party was indeed run honestly. Okay, so it means that if there is someone cheating in the set you open, you are going to see it. Okay, so the verifier is able to see with reasonably good probability if something was off. And because of that, we turn the multi-party computation thing into an identification protocol. So that's the high-level idea. Okay, and what makes it hard to understand in general is that when you take complicated problem, this relation we are going to look at, this R of X and W, is pretty difficult to understand. And when you run this multi-party protocol, it can be quite convoluted and hard to understand if you just look at it. So putting this complicated protocol together with the multi-party computation in the head idea makes the global thing a little bit hard to understand if you are not a specialist. So in order to understand this better, what I'm going to do is I'm going to take cases where the multi-party protocol itself is so simple that you will not need to make any effort to remember the multi-party protocol itself. So you will be able to focus on what's happening when you turn it, when we transform it within the MPC in the head paradigm into an identification protocol. Okay, so let's go for the easiest thing first, and let's work with discrete log. So you all know discrete log. So we are in some finite group, preferably of prime order, and we have an instance of the problem, which is y is equal to g to the x, where g is the generator of the group. Okay. So now, what is a natural way to share this exponent x? You could share it using a XOR, but then it would make the protocol very cumbersome. So instead, we are going to share it just using addition. So we write the secret x to be x1 plus x2 plus xn. So each party has one value xi, and this addition is of course modulo q because the order of the group is q. So if you compute g to the q, you just get 1, so it would not contribute. Okay. So now I claim that if you have such a sharing for discrete log, it's extremely easy to do a protocol that will verify it. So what you do is every party just outputs g to the xi and give it out as yi. Okay, so this is easy. And once you have done this party can, all of them can look at the values of y, multiply them together, and check that the product is indeed y. And if the product is indeed y, it means that the values that the product is equal to y, so it means that g to the sum of the exponent is equal to y, which works. Okay, there is something a little bit subtle here, is that it's extremely important for these to work and prove anything, that everybody outputs his value at the same time. Okay, to show why, assume I am the last guy, yn, and somehow I lost my share xn. And I still want the protocol to work, because I am dishonest. How can I do that? Well, I'm just going to wait until everybody has published their public part, and now I am just going to recompute the missing share that would make the product be y, which is very easy. You just compute y and you divide by y1 up to yn minus 1. And of course, the verification is going to work. So if I am able to, kind of delay my thing, then it will not work. Okay, so it's pretty important that, that people cannot change their secret value after the other have published stuff. Otherwise, we are just in trouble. Okay, good. Well, still, if there is one such cheating party, if at some point I ask the cheating party to display its secret, it will not be able to do it. So everything is not lost. But there are some things to be checked. Okay, so how do you transform this multi-party protocol into an identification scheme? Well, it's easy. You have now the prover and the verifier, and you do what I said before. So the prover starts by just sharing in a purely random way the value x. And then he runs the protocol in its head. So every virtual party just compute yi, and it just, here we are not even committing, it just outputs the values of y. Good. Once this is done, the verifier might be a little bit suspicious and say, okay, maybe the product is valid, but someone did cheat, so I want to make sure that things are good. So what I'm going to do as a verifier is I'm going to pick one random position, and I'm going to say, okay, now all of you, except this one guy, show me the xi's you had. And then you check that all the exponentiation for the people I have asked to open their party, their secret, I check that the exponentiation is valid. So it means that all the people I have seen are honest, so there was at most one person that was dishonest during the execution of the protocol. Okay. But since I chose the person I asked not to open randomly, if there are n people, my chance to not see that someone is cheating is only 1 over n. Okay, so it's hard to cheat. Okay, it's not enough for a signature because n has to be reasonably small for the protocol to work. So for a signature, you have to do that, but repeat it, basically. For an identification scheme, you have to repeat. You all know this basic principle of identification. If there is a challenge response thing and I have one chance in 2 to answer, of course I will pass the first test, or maybe the second, or maybe the first 10. But if you ask me 100 questions consecutively, the probability that I win is extremely low. It's 1 over 2 to the 100, which is negligible most of the time. Okay. Good. So this is the basic idea. But the problem of with this idea is that this protocol is very costly. You have to send all the Ys, and it uses up a lot of space. And you have to send all the Xis except one, so you also have to send a lot of space. To send a lot of, well, a lot of space. When you look at the signature, it's going to be very big. So how do we optimize this? How do we make this smaller? And these are extremely important techniques which are used all over the place in multi-party computation. So I want to look at them now. So the first thing you do is you don't want to display all the values of Y. Because if you do, it's going to take a huge space just because one group element is a big thing. So instead, you just commit to this value and you just produce a hash of all the Ys. Okay, good. So this makes the first part of the communication very small. Now, the verifier does the same thing. He says, okay, open everything except one guy. And now what you do is you send all the Xi, so this is still big, we will improve it later. You send every Xi except one, and for these Xi, you can compute the corresponding Y. And the missing one, well, I already explained how you compute it. It's just Y divided by the product of the other. So now, after receiving all the secret except one, you can still recompute all the public values. And once you have recomputed all the public values, you can check that the hash is the same as what it was in the first step. And because the hash function has no collision, this protocol is doing the same thing as the one before, so it's giving the same security as the identification protocol, but it's smaller in terms of size of things you transmit, which is a very good point for us. Okay, but still, the X part is big, so we want to get rid of this X part and make it small. Okay, so how can you do that? Thankfully, there are some tricks available out there that permit to do this, and the trick is to use what is called a puncturable PRF. So PRF means pseudo-random function, and you want to use that to compress x1 up to xn. Okay, so first I'm going to explain how the PRF works, and then we will see how we can puncture it, so to open everything except one value, and then we will see how we can make it, how we can use it to share what we wanted to share. So the basic idea is to start from a construction called the GGM construction. So it's, okay, I'm forgetting the names as always, so just look it up. Bear with me, sorry. I'm very bad with names and sometimes I just forget. So it starts with Goldrash, but I forgot the other. Goldrash, Goldwasser, Mikali, sorry. Okay. So what you do is you start with what is called a seed, and we call it the seed of the root because it's we are going to create a tree, so this is the root of the tree. So once you have a seed, it's a string which is of size, let's say, comparable to the parameters, to the security parameter. There are subtleties in how you do the computation, but I'm going to skip them today. So you start from the seed, and you use a left and a right function to create two sons, which I called S0 and S1, which are just going to be below the root, and which are going to be, if I'm using pseudo-random function to do this, these are going to be two pseudo-random values derived from the initial one. Okay, so I get these two things. And now I do the same thing. I'm going to take S0 and derive it into S0, S00 and S01. And I'm going to take S1 and split it into S10 and S11. And I'm going to do that again and again and again. And if the number of players is the power of 2, which makes things a bit simpler, at the end, at the bottom of the tree, I have 2 to the n values, or 2 to the t values, sorry, using my notation. Okay, good. And now, well, this is very compact because it can be represented by a single element, which is the value of the root. You can just re-expand and get all the rest for free. Good. Except that I don't want to send everything at the end. I want to be able to send everything except one value. So how do you do that? And that's where the magic comes. There is something extremely nice. Assume that, for simplicity, that the value I don't want to send is the last one. And you can really do the other cases yourself. It's just using the symmetry in the trees, it's the same thing. So if I want to send everything except the last one, what I'm going to do is first I'm going to send S0, because when I send S0, I am sending the left part of the tree for just one element. Okay, good. Now I cannot send S1 because that would reveal the last one. But instead I send S10 because this gives the next quarter of the tree. And then I send S110 because it gives 1/8 of the tree. And for a cost which is only logarithmic in n, with only t elements, I send everything except the final value. Okay, so there is a compact way to send everything except one value. Okay, if the value you don't want to send is somewhere in the middle, you just follow the path to the root, and you just open the siblings to the path, and it gives the same thing. Okay, so you can transmit everything except one value for the cost of log n. Okay, perfect, except that there is a little problem. If I take all the nodes at the bottom and add them together, there is no chance it's going to be the secret I wanted to share. These are just random values, so they cannot add to the secret. Okay, not a problem, I'm just adding an offset, which is whatever is needed to make this random value, which is the sum of everybody, into the secret. Easy for me, I just have one subtraction to compute. Okay, good. So now, if I go back to my protocol, when I want to send everything except xi, instead of sending all the value but one, I just send these t internal nodes of the tree that will allow the recipient to recover everything. Okay, so now the communication is much better, and still you have what you wanted. Good. So let's go for further improvements. So the next improvement is a technique that is called the hypercube. And the hypercube allows to do the same thing, the same quality of identification for lower cost in terms of computing. So why? Because it's going to allow us to do the same thing, the same checks, but by using much fewer exponentiation. So in order to benchmark this, I go back to the protocol and I ask myself, how many exponentiation did I have to do here? Basically, I had to compute x to the g to the xi for n minus 1 values. So the number of exponentiation I had to compute was quite big. Okay, so let's try to make this smaller. So instead of having something in terms of n, I want to make a number of exponentiation in terms of t. And how do you do that? Well, if you look at x, which is the sum of all the nodes, I am going to split the sum in different ways. So let's focus on the let's say on the first bit of the secret. So what is it? When the first bit is 0, I am on the left part of the tree. When the first bit is 1, I am on the right part of the tree. So now let's sum everybody in the left part and sum everybody in the right part. What I am claiming is that if I take the sum of the left tree plus the sum of the right tree plus the offset, it's going to be a sharing of the secret. Of course, because when you sum everything, you get a sharing of the secret. It doesn't matter how you group, the sum is the same, so you still have a sharing of the secret, but now you have a sharing in 2 parties instead of n. Okay, you might say this is making things worse. Well, yes, but no. It's making things worse at first glance, but now I did that with 1 bit. If I move to the next bit, I get another sharing of the secret. And to the third bit, yet another sharing. And all these different sharings are independent enough. They are not fully independent, but it's good enough. They are independent enough that I can, in fact, run t copies of the protocol with 2 parties. So it gives me the same level of confidence, 1/2 to the power t, which is the same number as 1 over n. Okay, but how many exponentiation do I have to do now? I have just to do one exponentiation in every step. So the total number of exponentiation you compute when doing that as a verifier is only t instead of n minus 1. So it's much fewer. So that's why it's better. Okay, but asymptotically, you still have something big to compute because there is this tree of size 2 to the n, and you still have it there. So we are just getting rid of the expensive exponentiation, but still have to do some computation with a large number of time. Okay, so now that I have seen all this optimization for the discrete log, it's time to move to something more interesting. So you might ask, why do I say that the discrete log is not interesting? Because with the discrete log, there is a better protocol, which is what is used in Schnorr signature, where you can just send one thing, get one question which can be arbitrarily long, very long at least, compared to the security parameter, and just give one answer and check, and you could only answer one of the many questions. So it would be much more efficient in every regard. Less computation, less commitment, everything would be better for discrete log. So it doesn't really make sense to do what I have done, except that it's easy to follow and it gives us a good warm-up for what I'm going to do now. Okay, so what I'm going to do now is I'm going to look at isomorphism and group actions because this thing have been proposed as post-quantum problems that can give post-quantum security, which is, as you know, not the case for discrete log. Discrete log, when you go to quantum computer, if you get an universal quantum Turing machine, you can break discrete log using Shor algorithm and all security is lost. Okay, so we need something else. Oh. So let's go back to the 80s, and at the time, people had the idea that maybe we could use isomorphism of, let's say, graphs to do crypto. So what is graph isomorphism? Well, you have an example here. I claim that these two graphs are indeed the same. So, well, you can see geometrically, just take one node in the right corner, move it inside, and you will see that it's connected to all the outside things and that the connections are exactly the same. Okay, you just have to give numbers to the nodes, and if you match the number correctly, you see that these are indeed the same graphs. Same number of nodes and same connections between the nodes. Okay, so people had in mind that we could use graph isomorphism to do identification scheme, and this was proposed, and this is very nice. The only problem is that nowadays we know that graph isomorphism is dead, at least where crypto is concerned, because there is a quasi-polynomial time algorithm to solve the problem. Okay, so we cannot hope to do any crypto out of this. So instead, we are going to use something a little bit more general, which is isomorphism. So how do I represent this? So I'm a little bit formal here, but it's going to be easy. So I take a set of objects. The objects are whatever you want. Okay, they could be seats in this room, they could be anything, it doesn't matter. And then there is just the option of undefined that I am adding, because sometime I might want to have some result to be undefined, so I'm just adding it there. Okay, so now I'm going to have some functions from the set of object together with the invalid object to itself, with the constraint that the image of invalid is always invalid. And I'm saying that two objects are isomorphic if there is a pair of functions that just send one to the other and backward. Okay? So that's the only thing I'm asking for. Okay. So, and because you can compose this map, if I have a map that sends a value from here to there, then from there to there, then from there to there, there is a map that goes there. Okay. And so I have a very simple case of I have a monoid mathematically that acts on this object, and I want to know whether there is a path or there is something that goes from this object to this one. Good. And we are often going to look at a special case where we have a group. And when we have a group, things are simpler because every map is going to have an inverse, so you don't need the two conditions. If there is a way to go from there to there, in a group, you can go back. And so that's why for isomorphism, you might have cases which are undefined. For group action, we don't, because there is a group, so if you can go forward, you can go backward all the time. Good. So yeah, I just said that already. And we are basically, when we look at group action, we focus to a specific case where it's possible from every object to go to every other object. So you can either say that the action is transitive, or you can say that the group action has a single orbit, or whatever. But this is a nice case, because if your set of objects is split into several distinct subsets that can never interact, well, you are somehow reducing the security level, because you only have to focus on one of the set to look at the problem. So that's why it's nice to look at this special case. Good, but this is not always the case. Some people have been proposing stuff which are based on isomorphism where you don't have a single orbit. Okay. So to make things simpler, let's focus on group actions. So a few things should be easy in this setting, computationally easy, and a few things should be computationally hard. Because if nothing is easy, if everything is hard to compute, there is no way I can make an efficient protocol. And if everything is easy, there is no way I can get security. So I need some operation to be easy and some of them to be hard. Okay, so typically what should be easy? Well, given a map on an object, I should be able to find where I'm going, starting from this and applying this map. If I can't find this, it's going to be painful. So given two maps, I should be able to compose them. And if I am in the symmetric case of the group action, given one map, I would like to be able to compute the inverse map. Okay, and on top of it, I would like to be able to sample a map at random from the set of all maps, because if you can't do that, it's going to be painful to do all the things I need to do. Good. So what should be hard? Well, if I have an equation of this form, so I give you two objects, O and O prime, and I claim that I know a map from one to the other, it should be hard to recover the map. Because if you know how to recover the map, well, all security is lost. And sometimes people also want to be hard to compose the map with another object which is neither O nor O prime. And we are also going to need that. So the first thing is usually, is the inverse problem, and the second one is called the parallelization problem, basically. So you would like to form a nice rectangle. If you know that you can go from there to there, where can you go from there? If you can do the parallelization, then you can break this. Okay. So for simplicity, I'm going to ask for all this set to be finite. Because, well, computationally, working with infinite sets is painful. And if you have infinite objects to represent, it's going to be hard to say what is the size of the signature. So let's assume that everything is going to be finite. Good. So there are a few examples. So graph isomorphism, well, no, because it would not be secure. But there are a few other candidates that people have been looking at. So there are something called isomorphism of polynomials, which is used in multivariate crypto. You have code equivalence, you have tensor isomorphism. And the last two I am putting with a question mark, because lattice isomorphism, while very nice, if you want it to be mathematically clean, you have to work with an infinite set. And I don't really like infinite sets. So in order to work with finite sets, you have to do stuff. So let's look at this reference I gave here. And for isogenies, which is something that lots of people love in post-quantum crypto, especially a few people I see in this room, it's harder because in general, given one curve, it's hard to pick a random isogeny and be able to compute it, so you have to work a bit. But apparently there are some very recent results including these ones that use the attacks on SIDH to be able to compute isogenies in a more efficient way somehow, without having to rely on easy to compute special cases. Good. So now let's go back to picture and stuff that would be easier to understand. If you didn't understand all the formalism, all the mathematical part about what I have done before, trying to formalize a group action, it doesn't matter. Okay, for what I'm going to do now, just remember that I can apply some function to some object to get another object, and I have a secret public key pair where I give as public key two objects, the O1 and O0, and my private key is a map that goes from one to the other. Okay, and I want to prove that I know the map. Okay, so there is a standard approach that people have been doing, and this standard approach works as follows. What you do is you take a random map and you apply it to O0, and you get some random object. If you apply a random map to the reference object, you get something random. Good. And now the verifier just choose a single question, 0 or 1, and send it to me. And if the question is 0, I just send back the random map I had. And if the question is 1, I send back the random map composed with the secret key. In both cases, I have some random map I am sending back, assuming it can be represented in a way that is oblivious of this composition I have done. And what the verifier can do is check that this map phi prime, composed with the object B, corresponding to the bit, is indeed equal to the random object. Okay? And the thing is that you cannot answer both questions if you don't know the secret. Because if given a random object, I know the answer to both questions, I can just use the group structure to compose this thing to cancel out phi r and recover phi. So if I know the answer to both questions, I can recover the private key. So if I don't know the answer, it's not possible for me to answer both questions. I can answer at most one of them, which means that if I'm cheating, you catch me with probability 1/2. But in order to turn this into a signature scheme, I have to repeat this many times, at least 100 times, which might be a lot. Okay. So that's where we are going to use this multi-party in the head to make this more efficient, to require fewer repetition and everything. So how can I do that? Well, remember in the discrete log, I was sharing the secret as a sum. So now I'm just going to share the secret, but as a composition of random maps. Okay, except that if I just compose random map, I get something random, which might not be the right one. So I'm just adding some offset, which is just the map you need so that the composition is the secret. Okay, and now there is an easy protocol to verify this. In the protocol, you start from the initial object O1, and the first prover applies his secret to O1 and gets O2. And because it's hard given two objects to recover the map, nobody can recover phi1, so there is no problem. And the second prover now applies phi2, and the third prover applies phi3, and so on and so forth, until the last prover gives this map, gets an object ON plus 1, you add the offset map, and you should go back to O0. If you don't, too bad, it didn't work. And everybody should check the last step. Okay, now we have this easy protocol, the easy multi-party protocol. We can convert it as we did before. Well, almost. We just need a little trick. That's the only thing. So what is a little trick? Remember, to compress the signature, we needed to be able to take all the views and just commit to them, and then we needed to verify this. But the guy that verifies is going to know all the secret except one. So from all the secret except one, is there a way to recover all the internal object, which will be in the view, and check it? Well, yes, there is, because if you know all the secret except the secret number I, you can go from O1 to OI just using the same computation as we did when running the protocol. But now, for the second part, the second half of the object, you cannot do that. But what you can do, because we are in a group action, you can start from O0, compose phi delta backward, and backward again, and you will get all the object up to OI plus 1. So you still get all the object. The only thing that you are not sure of is whether there is a map, if someone knows the map, that will connect OI to OI plus 1. But for the same reason as before, we don't care. Okay, so we can reconstruct the full view, we can check it, and we get something nice and efficient for this multi-party computation in the end. Okay, good. Of course, we want to optimize and use the puncturable PRF. So what you do is, as before, you do the tree and you get random numbers. And once you have these random numbers, you need to turn them into random maps. But, you know, assuming that you have done your work correctly and it's easy to sample from the set of map at random, this should be doable in a nice way. And so we can, again, compress the sending back of all these maps without having to send all of them at the same time. Good. So this is what we can do with multi-party computation in the head for this problem. But let's do the full thing and turn this into an identification scheme and then discuss a little bit about signature. So what's happening here is that, as before, there is a prover that knows the secret. So the prover just takes the secret, split it into a composition of random maps, and run in its head everything, all the protocol, and commit to the view at the bottom here, and send this to the verifier. So the verifier picks at random one element n, send it back to the prover, which send back the puncture key, so the key that is giving you everything except one object. And now the verifier can recompute the internal view and check that it is indeed correct. And what we know is that the verifier has a probability 1 over n to be to make something. Well, a cheating prover has a probability 1 over n to confuse the verifier and make him think that the interaction is valid even when it is not. Okay, good. So this is very good for an identification scheme, but for signature it's not quite good. Why? Because, okay, all this computation should be doable. So for this computation to be doable, n has to be not too large. So if you look at what people are doing all over the place for MPC in the head, you can expect n to be, let's say, up to 1 million, maybe a bit more if you are really optimistic on the performances, but okay, 1 million is a big number of things, so you still have a reasonably good, a quite big protocol to execute, so it's a bit costly. But from a security point of view, it's not good enough. Because for an identification scheme, I have 1 chance in a million to succeed. Okay, I just run these 2, 3, 4 times sequentially, and you are happy that I couldn't have been able to cheat. So to identify, let's say, at the bank automat to withdraw money or something, that would be good enough. But for signature, 1 chance in a million is not good enough. You need something stronger. So we still have, despite the n here, we still have to do repetition of the protocols. So we have to do, for a signature, we have to do several copies of this protocol into the same signature. Okay, and this is why the signature, when we look at MPC in the head, are still quite big, and the bigger part very often come from this puncturable PRF. Because even if you have only a log n element, they are still reasonably big. So it's not the signature are not very small. I mean, compared to what you could do with elliptic curve, for example, it's much bigger. So for elliptic curve, we could do signature with half a kilobit or something like this. For MPC in the head, the sizes are much bigger. It's above 6 kilobit right now. So it's still quite big. Okay, if someone made it into 5, just interrupt me, but it's still big. Okay, good. So there is one last thing I would like to speak about, is that this is a very nice thing, but it turns out that there is a way to just use the puncturable PRF to do the same kind of identification, but without using MPC at all. And it still gives you the same security level and the same kind of things. So it's nice to know that there is this alternative technique. Okay, so how does it work? So, well, basically there is still a public key, private key pair. Just note that in the MPC case, I use this relation. The object 0 was the image of the object 1 by the map phi. And here I just reverse the relation. It doesn't matter, it's just because the notation are less cumbersome. It's just to make the notation look nice. Okay, and there is no reason to choose one direction or the other. It's really irrelevant. So what you do now, for this scheme, for the identification, we are going to do something extremely similar. So we compute a seed tree as before. Okay, so it's possible as before to open everything except one node for a very low cost. And now, instead of doing this sequential process where we took the first element and then applied the first map, then the second map, then the third map, we just apply each of these random maps to the object O1. Okay, this is what we are doing. And then we just commit to all that stuff by hashing it. Okay, and now what the verifier is going to do is going to say, okay, you have done that. I know that if you have been honest in your internal generation, whether you know the secret or not, you should be able to display all these maps that would reconstruct the internal thing. So what I'm going to do is, instead of asking for that, I'm going to ask you to open everything except one position, and for this missing position, show me that you can relate it to the object 0 instead of relating it to the object 1. I know that if you didn't cheat, you should be able to relate everything to the object 1, but if you don't know the secret, this will not help you to go to object 0. So now just show me in one place that you can go to object 0. And so how do you show that? Well, you take this map that you had internally phi I, and you compose it with the secret, and it gives you another map, and it's very easy to recompute from this map on object 0 what the target would be. Okay, so now you can reconstruct everything that was internally, but there is no way for someone that doesn't know the secret to know both the tree, the full tree, and the object 0. So someone that doesn't know the secret can only cheat in one position, can only know the map from O0 for one position, if he has to know the map to O1 for all the other position. Yeah, so I can choose if I want to cheat. I can say, okay, I'm going to cheat in position 100, but if I run the protocol and you ask me to open something else than position 100, then I lose. So my chance of winning is here again 1 in n, which gives you the exact same soundness as with the multi-party protocol. Okay, somehow this seems a little bit simpler than the MPC in the head, but it's really using the same ideas. So maybe, I don't know, but maybe there should be a way to view this as a multi-party computation anyway, but I don't know exactly how. Okay, so that would be an open question to reinterpret this in a different way. And so basically this ends my presentation, because I wanted to leave a little bit of time for question, and I think I'm happy to take any question now.
Do you have any question? Okay, I have one.
Yes.
At the beginning, you showed us you share X using an out-of-n secret sharing scheme. Right? Yeah. Next.
This one?
Yeah, this one.
Yeah.
Does it make any sense to consider any kind of secret sharing, or maybe K out of n secret sharing or linear secret sharing to share X?
So I didn't speak about it, but yes, it's possible to use. So this is a very stupid additive secret sharing, and there are lots of other secret sharing. I think everybody in this room knows Shamir secret sharing, for example. And it turns out that yes, you can do MPC using other kind of secret sharings, and depending on how you design the protocol and stuff, you might get some optimization out of it. So there has been a lot of work by Rivin and Feneuil on this. I think you can find their papers on ePrint, and they explain what they can do. Okay, they did it for code-based signature, but they are using Shamir-style secret sharing to do the thing in a different way. So basically, what's the nice thing about having a Shamir secret sharing? The nice thing is that if I have, let's say, so here basically you need n-1 share, you need all the shares to be able to open. So assume you do something slightly different, where with k out of n you could open, for some value of k, then I could open without revealing any secret, I could open k-1 position. Okay, but it means that the combinatorics of how many questions the verifier could ask is becoming bigger. Because here the combinatorics is just one value. If there is a larger possibility of subset of a given size that could be open, then it makes the set of questions much larger. So, but you have to pay the price because the verification becomes different and sometimes more complicated. So it's not completely clear which is better when, and so there probably is a lot of room to improve this stuff again, and it would be a nice question of whether we can do something like this in the discrete log example. I didn't really try, but it might be a fun thing to try, yes.
Thank you. Any other question? Okay, let's thank again.
Okay.
Nestor,
Thanks.
thank you. So now we move to the classes. To the next talk. The talk is efficient SIDH based signature. Yes, SIDH, and the talk will be given by Mattia Veroni. Okay, thank you.
Thank you. Okay, so it's a wrap. So thank you all for listening to this talk and to the CIFRIS conference for inviting me. So today I'm going to talk about a result that we achieved with Sam Gantus and Federico Pintore, who's in the audience. I'm Mattia Veroni, and I come from Norway. So actually it was a bit fun because there were minus 18 degrees when I left, and I arrived at plus 18 degrees, so I couldn't wear a suit anyhow today. So what am I going to talk about? First, how to get signatures, isogeny-based signatures, and in particular, the historical context behind SIDH signatures. So that are based on the SIDH identification protocol. And then I'm going to talk about a new scheme, which is not broken, luckily, which is Sigma Secure. And then I will talk about the results we achieved in this paper. Then finalize the talk with some open questions, open problems, and summarizing our results. So I assume you all know what zero-knowledge proofs are and how important they are today. So they have plenty of applications. Those of you who are interested in blockchain know that zero-knowledge proofs are proposed today to either achieve better security, if you think of Zcash, or even to achieve better scalability, if you think of Ethereum 2.0. But for what concerns us is that if you use a zero-knowledge proof to show knowledge of a secret key that corresponds to a public key, then you have an identification protocol. So at the basis, if you have an identification protocol, we know we have Fiat-Shamir transform to turn this identification protocol into a non-interactive one that then gives us a digital signature, which is a hot topic for today's internet. In isogeny-based cryptography, we have different families of Sigma protocols. The first one, which is the one I'm going to talk about, is the SIDH-based one. And we have seen today that SIDH is broken. So why am I even talking about this? You will see in a few slides. The nice thing of this family of isogeny-based protocols is that they use primes that are very nice in terms of computational costs, in the sense that they use small degree isogenies or a chain of small degree isogenies in order to get good enough computation time. It's still bad compared to other post-quantum families, but using these small degree isogenies is an improvement or gives us very good results in terms of computational complexity. Then we have the C-side-based family. So two of the main exponents are C-sign and C-fish, which are based on the C-side group action. So there we work over FP curves defined over FP instead of FP square, as we do with SIDH. But we have a full group action in that case, which we don't have in SIDH. And the way of achieving actually the key exchange was to pull a trick and communicate some extra information, which turned out to be fatal for the security of the scheme. Then we have KLPT-based signatures, like the Gabriel-Petit-Silva and Ski-sign signature. I mean, calling it KLPT-based is maybe a bit of a stretch, but they use KLPT in the response computation. So we can call these KLPT-based. And then we have generic zero-knowledge proof systems. But today, what I'm going to describe briefly, first from a historical point of view, and then from an applicable point of view, is SIDH-based proof of knowledge. So SIDH was first made public in a paper from 2011, and then together with Psych, so the supersingular isogeny key encapsulation, we also had an identification protocol that was in form of a zero-knowledge proof, actually. This is still a paper from Defeo, Zhao, from 2014. And then from here, two new schemes came out a few years later that used the SIDH identification protocol deeply. Problem is that last year, attacks to SIDH came out, and well, this would seem to be the end of all SIDH offspring, but actually this was not true. So as I mentioned before, the problem with SIDH was transmitting some extra information that was allowing the key exchange. And in particular, this extra information was the action of the secret isogeny over a torsion subgroup of the elliptic curve. And using this action, the knowledge of this action, was actually possible with this attack to recover the whole secret isogeny. The thing is that, as of now, we don't know how to solve this problem if we don't give distortion information. So new protocols came out recently that mimic exactly what happened in SIDH, but avoid sending the torsion point information. And without these, the schemes seem to be secure. And in particular, one that was published this year and then was used to achieve a sort of computation of a random elliptic curve of a known endomorphism ring, which is crucial for security, was sigma secure. So as Luca knows, like, isogenists love puns, and it was suggested that this secure thing was pronounced with a British accent because it's spelled wrongly. So if you see me do this, since I'm bad at accents, you know, I'm trying my British accent. So this is Sigma Secure. So what is Sigma Secure? So since our scheme is based on this one, I first need to introduce you to the scheme itself. The first building block we need is a commitment scheme that takes a message and a random element and produces a randomized commitment of the message. And then Sigma Secure allows a prover to show knowledge of a secret isogeny between two curves E0 and E1, given that this isogeny is of a fixed degree D, and prove knowledge to the verifier V without actually leaking the secret isogeny. And how is this done? So the first difference between SIDH and this identification protocol is that the challenge is ternary. So we have 3 bits instead of just 2. And in case so commitment isogenies are computed, randomly computing or randomly selecting a subgroup of the torsion subgroup of E0 of order L to the n. And then 2 extra elements are sampled, and they are used to commit to the elliptic curves that are the images under these vertical isogenies that you can already see on the left. There is also a commitment made on the right side of the diagram that you see there, but it's for now hidden because it will be shown in a few slides. Once the commitment has been produced, it is communicated to the verifier, whose only contribution to the scheme is to provide the challenge. And this is a ternary challenge, so the challenge space is quite small since we only have three elements. The challenge is sent to the prover, and depending on the challenge, the prover reveals one of the edges of the scheme, the diagram that I'm going to show, which is then used by the verifier to actually check that the commitment corresponds to the opening to the commitment corresponds to the commitment that was made, and that the isogeny that is revealed actually takes from E0 to the committed curve. So in case of a challenge equal to -1, the left doesn't. The left side of the diagram is communicated. If the challenge is 1, then we open the right side of the diagram, and none of these 2 vertical sides actually use the secret isogeny to compute the response. The only point at which we need to use the secret isogeny phi, so the knowledge of the secret, is to compute the isogeny between E2 and E3. So you can easily see that this protocol can be, so maybe you cannot easily see, but if you have the full diagram, as on the right, you can extract knowledge of the secret. And I'm going to talk about this in the next slide. So first of all, since we have three options for the challenge and only one uses a secret, we have 2/3 of cheating probability, or the prover has 2/3 probability of cheating for a single run of this protocol. And in particular, if the verifier is given all 3 edges of the diagram on the right, it can extract knowledge, so it can extract an isogeny from E0 to E1. But the thing is that we cannot really guarantee that this is exactly the secret isogeny phi, because given the extractor that the protocol provides with the security proof, we have this L to the 2i as the degree of the extracted isogeny, and we would like this I to be 0 in order to extract actually the secret isogeny. But this is not what we can achieve with Sigma Secure. So the soundness error of the scheme is 2/3, just because, as I mentioned, only in one case out of the 3 ones for the challenge, we actually use the secret isogeny, the knowledge of the secret isogeny, to produce the response. So to make this actually secure and anyhow meaningful, we have to repeat many times. And in particular, as Antoine mentioned before, we would have to repeat t times if the soundness error was 1/2, so that were lambda times if the soundness error was 1/2. But here, since we have 2/3, so in 2 cases out of 3, we don't need to use a secret. We actually have to do this more than lambda times. So t is lambda over the logarithm of 2/3, the closest integer, well, the upper integer to the ceiling. And the thing is that when the design, so we didn't design this protocol, as I mentioned, other authors made this, and they really wanted to achieve statistically special honest verifier zero knowledge. So what they wanted to do was for the verifier to be enabled to actually extract the knowledge, so the secret witness in the Sigma protocol, but not just relying on a computational problem, really just achieving pure statistical indistinguishability. So it turns out that this is a bit of a stretch for the application we have in mind, also because the authors of this protocol cannot just achieve the full protocol with the SIDH square that you see here on the right, but they have to create this ladder in which they combine different SIDH squares built on top of each other. And then for the full protocol that they have in mind to generate a curve of a non-endomorphism ring, they also need many parties to compute these SIDH ladders side by side. So we go simple. Since our goal was to produce a signature scheme that was SIDH based, even if SIDH seemed to be dead, we could just get away with computational special honest verifier zero knowledge. But since we are talking about a computational problem, what is our computational problem? So we need to introduce this hardness assumption, which is the decisional supersingular product problem for the SIDH square, which basically states that if you're given a curve, 2 curves, or well, all the curves in the SIDH square is 0, E1, E2, and E3, and you're given an isogeny between E2 and E3 of the degree that you expect this isogeny to have, which is the same degree as the secret isogeny phi, you shouldn't be able to tell if this isogeny phi prime is actually part of an SIDH square, meaning that E2 was produced using an isogeny of degree coprime with phi starting from E0, and the isogeny between E2 and E1 and E3 is the matching isogeny under phi. So you shouldn't be able to tell whether the bottom edge, without having the vertical edges, is part of a full SIDH square, or if it's just a random isogeny of the degree that you want it to have. There are some technicalities, but the basic idea is this one. And we have this proposition, which is a diminished or a weaker result compared to the one that in the original protocol, just because we don't want or we don't need statistical honest verifier zero knowledge, but we can just get away with computational. And so we have this proposition that tells that if the decisional supersingular product problem is hard, and if you use a computationally hiding commitment scheme, then the result is a computationally honest verifier zero knowledge sigma protocol. So now that we have kind of weakened a bit the protocol that we were starting from, just because it had some extra results or extra strengths that we didn't really need, and by doing this we gain a bit in computational complexity. So this has some advantages at the price of a weaker zero knowledge flavor. Then we take this basic protocol and we repeat it t times. And as we know, if we have an interactive sigma protocol, we can use the Fiat-Shamir transform to remove the need for interaction by having a hash function simulate the challenge creation. So once the commitment has been made, you feed the commitment and the messages you want to sign to a hash function, you get a challenge out of it. So you don't need to talk to a verifier who has to provide the challenge. And if the hash function is a secure hash function, the prover shouldn't have a way of telling beforehand, before the computation is made, which the output of the hash function will be. So it shouldn't be able to guess the bits of the digest. And then, if you take the basic protocol that I just showed you and apply the Fiat-Shamir transform, you get a digital signature scheme which has a signature of this side. So 4 lambda t is the size that comes from the commitment part. We remove the challenge just because the challenge can be recomputed knowing the message and the commitment. So we remove it from the signature. And the rest is the size of the response, which is an estimate. So we take the number of iterations divided by 3. And what you have in parentheses is the size of the response for challenge equal to -1, challenge equal to 1, and challenge equal to 0. And the first thing I would like to draw your attention to is that the size of the response when the challenge is equal to 0 is quite larger than the size of the response in the other 2 cases. Not extremely larger, but it's quite larger. And this will be a key fact for one of the optimizations that we propose for the protocol. Because our case study in this paper was to start from this protocol here and apply and tune in some optimizations that are known in the literature. Not all of the results that we apply were known in the literature before we came up with the proof for that. And basically what I will talk about today is how to squeeze the size of these signatures here, which seem to be excessively large, especially if you compare to other isogeny-based protocols. I mean, without going to SkiSign, who has around 200 bytes, here we would have something like 65, 66 kilobytes, which is significantly larger. So how to take these numbers down? So once we have seen the sigma secure, then we talk about an efficiency study, where we try to gain efficiency in the size of the signature and also in the computation time. The first trick we pull is the commitment recoverability. So if you can remove the commitment from the signature, which means that the commitment can be recovered by knowing the challenge and the response, then you don't need to send the commitment. And the thing is that the original protocol that we started with was not commitment recoverable. So we have to modify it a bit. And in particular, we had to assign, so to move some of the items that were in the commitment to the response, still achieving a good result in terms of how many bits we save by removing the commitment overall. Because by sending this as a response, in case, for example, with the challenge equal to -1, the prover can retrieve the commitment on the left, so can compute C of E2, B3, but cannot compute the commitment C of E3, B3. So that's why we have to add it to the response. And the opposite happens if the challenge is 1, so the prover cannot compute E2, so cannot compute the commitment to it, so we have to provide it together with the response. While for the case in which the challenge is equal to 0, we can just remove E3 because it can then be computed from E2. And also the commitments themselves can then be computed by the verifier. So we don't need to send them along with the signature. So we omit or move some bits, but in general omit the commitment in the response. So what we can achieve is already basically halving of the signature size. And even more, if you decide to compress the points, because in the 3 cases we have to send points that generate the curve, you can compress these points and achieve even a further optimization. So we reduce the signature size of an extra 9%, more or less. And all the upcoming optimizations that we propose are now based on this result. So you will not see 48% anymore. You will just see like 8%, 6%, just because these are incremental improvements over this intermediate step. But you could consider every single optimization per se. But we don't have the numbers here for the specific optimization, but only to the sequential application of all of them. And then we have the trick of seed trees. So it's kind of like punchable PRF that Antoine mentioned before. The thing is that we don't have to puncture. So we really want to communicate all the seeds that are used to generate the commitment values B2 and B3. And these have to be communicated to the prover. So we don't need to hide any of these. We can simply communicate the root, the seed of the root, and then the prover can compute like as a cascade all the leaves in the tree that are used for committing. And we could do the same actually slightly more carefully with the reveal of the values Ri. Because if you let me go back a bit, in the point compression, when we have to send H, phi of H, and psi of G, we actually send the kernel generator. And we don't actually send the point, we send the coefficients that on a specific basis give you that point. So also these coefficients have to be produced at random for the vertical isogenies and have to be communicated. So you can pull a similar trick here, but you have to be more careful because you don't want to always reveal the vertical isogenies. So what you have to do is selectively open some of the seeds in the tree, but we have algorithms to do that efficiently. But just the improvement is not as sensible as it is when removing the need of sending the commitment values. And as you see here, we have an extra 8% in gain. So now the signature is from about 65 kilobytes to 20, say 22, 23 kilobytes. Even more, this is actually a fairly new idea because it was introduced only a couple of years ago. And the idea is this. If you have an identification protocol that has responses of different sizes, so not all of the responses that you have to transmit take the same space, you may want to reduce the number of challenges that result in a heavy response, and you would want maybe to increase the number of the short responses. So what you do in general is to increment the number of iterations, but in this number of iterations, you reduce the number of challenges that give you the unfavorable response, unfavorable in the sense of signature size, so a large response. So we have some study on this because the previous results were only for binary challenges, while here we have 3 possibilities. So we extend these results and we come up with concrete numbers for how many iterations you need to perform and how many unfavorable challenge bits you have to embed in the challenge string. And in particular, we come up with the concrete numbers for the different instantiations of this protocol that give you exactly M and K, where M is the size of the challenge string, and K is the size or the number of bits that correspond to the heavy challenge and the heavy response. And as a result, we obtain an extra about 5 to 7% in signature size reduction that takes us overall to a 71 to 72% reduction in the signature size. So we were starting from about 65 kilobytes, and we are now down to 19 kilobytes for CIFRIS 434. There is also the other side, which is always the negative side of isogeny-based signatures, which is the signing time. So if you take key sign as an example, because it's submitted to the NIST competition and it's considered to be the best candidate we have for isogeny-based signatures. Signatures are small, in the order of 100 to 100 bytes. But the signing time is quite unfavorable compared to other candidates because it takes about 2 seconds, 3 seconds on average. You can apply some optimizations, and it's likely that these optimizations will be introduced with the next round to take it to 1 second or around that time. But it's still a daunting task to compute a signature with isogeny-based schemes. What can we do with our proposal to reduce the signing time? So there are some facts that we could use and we could exploit in this scenario because we can parallelize computations, which is something you cannot do with keysign just because it's based on a completely different algorithm. So there's little to parallelize there, at least in the sense of isogeny computations, because here we have to compute many isogenies of small degrees. And why is it typical for SATH to be this parallelizable when you have many iterations? Because if you consider, for example, a base degree 3, so an isogeny step of degree 3, you only have 4 possibilities. It's always L plus 1, where L is the prime degree. But then, since an SADH isogeny, or an isogeny that is computed with SADH, doesn't have backtracking, the second step only has 3 possibilities. And also the next step to this will have 3 possibilities. So if you have to compute 250 isogenies, in our case for CIFRIS23, you will have to recompute, if you always compute from 0, all of these steps several times. So our proposal is to spend some pre-computation here to compute the steps that will most likely be, will have to be computed many, many times. And then with a simple modular congruence, you can check, given your kernel generator, which will the first step be, which will the second step be. So again, this is not a huge improvement because it's only about 8% of the total committing cost, not even the full signing cost, but it is something that can be taken into account. And a similar approach can be pursued when you want to, since you have to compute kernel generators first, starting from a coefficient, you will always use the same basis, the same torsion basis in E0, to compute all kernel generators for the vertical isogenies. And in particular, you have the first scalar multiplications as isogeny evaluations that will have to be performed many, many times. Because what we do typically to evaluate a long isogeny of degree 2 to the e, for example, you first decompose it into steps of base degree 2, and to get the first step, you have to perform E-1 scalar multiplications that take you to the kernel generator of the first step of the isogeny. And you have to do this for all kernel generators. So you have to perform many of these scalar multiplications. So you can even here parallelize or pre-compute. Since these computations will have to be run naively many, many times, you can just pre-compute all of these values, because they will always be used by all the committing isogenies or vertical isogenies, depending on how you want to call them. Again, this is a small improvement in the sense that, yes, we save 99% of the point doublings, but still there is only a small part of the whole overall isogeny evaluation that we can pre-compute, because the rest will not make sense to compute the whole thing as a pre-computation, because it will occur for one of the 250 isogenies. So it's better to just compute on the fly if you need a specific value. And this, so this is the updated version of the slides. So if you have a 3 to the 6, an isogeny of degree 3 to 6, this is what you actually do to compute this isogeny starting from the kernel R. So you go all the way down to the kernel generator 3 to the 5 multiplied by R. That gives you the kernel of phi 1. And then you fill out the graph, removing most of the scalar multiplications and instead introducing vertical isogeny evaluations, starting from the intermediate points. But the point I was making before is that what you have in the first line has to be computed for all kernel generators R. So if you can parallelize these scalar multiplications over the curve E0, this can save you quite some time. We have not implemented the scheme, so we don't exactly know how long signing will take, but you can think of just committing taking about 6 billion cycles, 6 billion CPU cycles, which easily translates to 2 seconds, 3 seconds. And this is only the committing phase. So our signing scheme is going to be outperformed both in signature size and in signing time by SkiSign. But what we wanted to, the point that we wanted to make with the scheme was that, first of all, SIDH is not dead, or if you communicate torsion points together with public key keys, but SIDH per se can still be used if you pay attention to avoiding transmitting this torsion point information. And also as a way of collecting several optimizations that allowed us to squeeze the signature quite sensibly, so by 70% on average. So to conclude the talk, we managed to reduce the signature size to about 17 kilobytes for the first NIST level of security. Still, this is quite unfavorable compared to other candidates. And there is also a lot of room for improvement when it comes to signing time. And maybe there are different ways or further ways to exploit the parallelizability of all the isogeny computations that happen here. So there are still plenty of open problems when it comes to SIDH-based signatures. One of these is that maybe if we could manage to prove knowledge of a set of isogenies instead of a single isogeny, then we could use some cut-and-choose techniques to decrease the number of times that we have to iterate the base protocol over and over. Then we could find a way to enlarge this challenge space, so to reduce the number of iterations, even if this works against us, because some of the optimizations that we propose exploit the fact that we have to repeat the protocol many, many times. And also, the major problem with isogeny-based crypto in general for signature schemes is reducing the signing time, which is still a valid problem, an open problem for the scheme we propose. So thank you for your attention, and if you have questions, I'm happy to take them offline, since we are on a quite tight schedule.
The last talk of this session is the group structure of elliptic curves over Z and Z by Massimiliano Sale and Daniele Taufer, I'm correct?
Yes.
And Daniele will give the talk.
Thank you very much. I hope you hear me. So there's only me between you and the coffee break, so I will try to not to kill you. Although the disclaimer is that this talk will be again on elliptic curves, so I hope you like them. But it will be more theoretical. So this is what I'm going to present. So this work is a joint work with Massimiliano Sala, which I guess you know very well. And this is indeed about the group structure of elliptic curve over Z modulo NZ, to make it simple, but I will tell you something about elliptic curve over generic rings. So the outline of the presentation is the following. So we'll give you a short introduction about the topic. How do we construct elliptic curves over rings? Why do we need addition laws, and what do they have? Why are them special? Then I will go to the main guy that we want to examine, so Z modulo NZ, and then we'll see some consequences, hopefully funny consequences. So I guess the majority of this audience knows about elliptic curves over fields. So K in this presentation is a field. Usually people from geometry like elliptic curves as smooth G0 curves with a projective point, with a specified point, sorry, and this point they want it to be k-rational if they want the curve to be defined over k. But in practice, what we do, what people do in cryptography and in many other fields, we consider the plane projective embedding of these curves. So we know that these objects may be embedded in P2 of k, and they are defined by the zero locus of a Weierstrass equation. And this special point that we want to always prescribe is the point 0, 1, 0, which is called point at infinity. So you know that those objects are usually depicted in various funny ways. If the field is finite, it's kind of a scattered cloud of points. If the field is R, it's like the nice picture you see everywhere in the textbooks. If the field is a complex, you have the complex torus. But all these objects come from the same equations, just over different structures. And the reason why we are so in love with these objects is because we can sum points, basically. So those curves are called abelian varieties, which means that if I take 2 points, which are solutions of the defining equation, I can add those 2 points and find a new one with the chord tangent rule, which is very cool, very studied, and a lot of very other positive adjectives. Although you see the usual construction of this rule, I mean, the usual graphical construction, there are also more algebraic ones that do not involve any sort of picture, but the graphical construction requires you to distinguish between cases where the 2 points are distinct, and when the 2 points are the same, and also to distinguish cases where the points are aligned with the infinity somehow. And this is not a big deal for people in engineering, but for mathematicians this is quite inconvenient because we like surfaces, we like Riemannian surfaces indeed, and we wish to have some way to define the addition law, so the sum between points, given by some open charts, and we would like those open charts to cover the whole space, and this is the usual way people try to define complex manifolds. And there is also, I mean, I could speak a little bit on top of this, but I let you, your imagination work. But also in cryptography, for example, it's convenient to have operations that are independent on the points that you are considering. So you want to avoid cases where adding points is much slower than doubling points or stuff like that. So strange behavior like that you want to avoid because you don't want to have sniffing type of attacks that counts the clocks of your CPU and try to exploit this to guess what you're doing. So the ideal situation would be to have just one uniform way to sum points over these objects, and this leads us to addition laws. So mathematicians, very good mathematicians actually, try to define this sum of points in a well elegant mathematical way, and the elegant way is what we call an addition law. So an addition law is a polynomial map that sends 2 points in the algebraic closure. So k bar is the algebraic closure of k. Not strictly needed here, but yeah, just to be formally precise. We want 3 polynomials, in this case x, y, and z, such that the sum of 2 points p and q is simply given by evaluating the polynomial x in p and q, the polynomial y in p and q, and same for z. And those 3 entries gives us the coordinates of the sum. So this, we'll see in the next slide that this would be the ideal goal, but it is unachievable, unfortunately. So we want it to be true at least on an open set, on a Zariski open set of E times E. And this is achievable, and if we consider some open sets that cover all the possible cases, and we plug them together, we collect them, such a set is called a complete set of addition law. Complete means that we can sum every point without exceptions by using one of the addition laws in the set. So this is the slide I was mentioning before. There is a very general theorem for any abelian variety, which says that if we hope to find complete sets of addition laws, well, we need at least the dimension of the variety plus one laws. So in the case of elliptic curves, we need at least 1 plus 1, namely 2 addition law. So it's impossible, but over the algebraic closure, it's impossible to have a sum defined uniformly by just one triple of polynomials. You need at least 2, and in fact, Boseman and Lenstra proved that 2 suffice. So it is possible to have a complete set of addition laws over elliptic curves by using 2 triples of polynomials. And the polynomials are not random, so they need to be homogeneous for some, if you think for a couple of seconds, it's trivial that you want homogeneous polynomials, otherwise, and you want to be homogeneous polynomial actually, otherwise the sum is not well defined because we are working over the projective plane. But what is not true at all is that, is not trivial at all, is that the b-homogeneous polynomials that you need, if you consider a minimal set of addition laws, they will be of degree 2, 2. So this means that they are in degree 2 in the first point, in the entry of the first point, and in degree 2 in the entries of the second point. So just for simplicity, this whatever I said so far is true in every characteristic, but for simplicity, let us assume that the characteristic is not 2 or 3, so we take the standard reduced Weierstrass model. And we also assume that the curve that we are considering do not have 2 torsion points. This is certainly not a good assumption for people liking super singular elliptic curves, but in classical cryptography, this is kind of a general assumption. So you usually want prime curves, so you don't want curve of order 2 times something. So for such curves, it is still true the theorem that we cannot make it to have a complete set of addition law with just one triple of polynomials over the algebraic closure, but it is true that we can have it over the base field. And this is what usually is usually interesting for people, for example, in cryptography. As Antoine said before, we don't like infinite structure so much. So if you work over finite fields, for example, and not over their algebraic closure, this addition law suffices, which means that if you plug the entries of the 2 points P and Q inside those huge, bad, ugly-like looking polynomials, you find the coordinate x, y, and z of your sum, x plus q. So what's new on this side? Well, Costello and others proposed a better version of these formulas by exploiting some symmetries that I will not investigate unless you ask me, so I'm happy to speak about that. So those formulas are more efficient to compute so they are the same polynomials, just rewritten in a more convenient way, which is cool. And we have a paper of this year showing that, in fact, you can obtain the same polynomial by computing this strange matrix here. It's an ugly matrix, I admit. So M is the matrix I'm referring to. It's ugly, but all these entries are polynomials of b degree 1, 1, so it's not as bad as it looks like, although it's not nice, I admit. And the x and the y entries of the points are computed by multiplying this M for the anti-commutator of x and y in the first coordinate and y and z in the second coordinate. And quite surprisingly, the white coordinate of the sum is in fact the determinant of this matrix. So now I know that people, at least mathematicians from the audience, are struggling to understand what is this matrix, and I must disappoint you. I don't know what is the meaning of this matrix. I just know that this computation works. And in a subsequent paper, same also from this year, we proved that the very same magic applies even for characteristics different from 2 and 3. The formulas are a little bit more complicated, but again, x and y are some matrix times the anti-commutators, and y is the determinant of the same matrix, just with ugly coefficients. So, whatever I said so far holds over any field that you like. We now want to extend this notion of summing points over rings as well. So the first thing we need is a notion of a projective plane over rings, which naturally extends the one over the fields in this sense. So we consider triples of element in the ring, but not every triple is fine for us. We want primitive triples. So we want x, y, and z, which by themselves can generate the whole ring. And we mode out, over the fields we mode out by non-zero element, over the rings we mode out by invertible elements of the ring. So what is the reason behind this choice? So this was first established by Lenstra. And the reason is that we want all the projections over every possible subfield to work well, in the sense that if we start from a proper projective point, we never want to be projected to some non-projective point over a field. So here I have an example. If you consider the point 033, this is not a legit projective point over 6 modulo 6c, because it projects to 0, 0, 0 modulo 3. So we want to avoid every possible bad projection, and the way we have to do it is by considering triples that generates the whole ring. Such a triple is called a primitive triple of element. And I know that this is kind of annoying because it's kind of not standard for people working over fields. And there is an even more annoying condition. We want that the ring satisfies some magic property. So let me first say that this property is satisfied by the vast majority of the rings that you can think of right now. But if I give you 1 minute, you can come out with a counterexample, I bet. So not every possible ring satisfies this property, but the property we want is that if we have any matrix such that all the 2 times 2 minors of the matrix vanish, and the entries of the matrix are primitive, so it means that we can produce the whole ring by taking all the entries of the matrix. Then from this matrix, I should be able to extract a primitive row or column. So this seems very natural. It is trivial over fields. It is true for every ring with a finite amount of maximal ideals. So in particular, it's true for every finite ring. But it is not true for every ring. So you can take the ring of integer of a number field with class number different from 1, and that would be a counterexample. Anyway, many rings, we are still happy. So how do we define the elliptic curve over such rings? So rings satisfying these magic properties. In the same way, we construct elliptic curve over fields. So we define the curve made by the projective triple, so primitive triple, up to invertible scalar multiplication. That satisfies the Weierstrass equation of the curve. And again, we want the discriminant of the curve to be invertible in the ring, which replaces the condition the discriminant not be 0 for fields. And in this paper, Lenstra in fact proves that if you consider such an object, which so far is just a set, and you endow this object with the same addition law I projected it in the slides before, these objects becomes a group. So it's in fact an elliptic curve in the same way we define it over fields, provided that you apply your addition laws and you extract a primitive combination of the addition law as a final sum. So this is a kind of a technical detail. Over fields, at least one of your laws always work. Over rings, this does not need to be the case, but a combination of the laws will work. So let's now dive into the Z modulo and Z case. So this ring is very easy. In fact, it is true that if you take any primitive matrix over such a quotient of the integer, there exists a linear combination of the rows So you don't even need the 2x2 minors to vanish. So a much, much stronger condition is true on this ring. So in particular, we can define elliptic curves over this ring. And it is very easy to see by the Chinese-Zermander theorem that if we start from Q1 and Q2, which are coprime, an elliptic curve defined over Q1, over the quotient Q1 times Q2 is simply the product of Q1, of the elliptic curve defined over Q1 times the product of elliptic curve defined over Q2, which means that considering n for the purposes of understanding the group is not really interesting, we can restrict to prime powers, which is what we do now. So if we start from an elliptic curve over z modulo p to the ez, we have a canonical projection into the underlying curve. And this projection is part of a short x-axis sequence, where we start on the left, we have the kernel of this projection, and on the right we have the projection. And in the generic case, which means when the trace of the curve is not 1, if you take a random curve, this will work. This sequence is a split sequence, which means that you can decompose the group of points of the curve as the group of points over, of the curve over the base field times this kernel of this projection. Why is this cool and almost solves the classification problem? Well, because we know every possible group arising from an elliptic curve over finite fields, more generally, so not only prime fields. So in particular, we know everything that every group that may appear in the box on the left. So we just need to understand the structure of the kernel of this projection, and this gives us the structure of every possible elliptic curve over z modulo nz. And the way we do it is like emulating the idea of points at infinity. So the expansion of points around infinity is kind of a classical topics leading to the construction of formal groups. In fact, every point at infinity may be written as x at 1 and some polynomial in the x. So that means that only the x rules the points of the infinity. So we can really describe the point at infinity by just specifying the x, and the z is just a polynomial function that is a polynomial depending on the entries of the curve. Again, it's not nice polynomial, especially if the characteristic is not 2 or 3, but it's a polynomial, so we don't care much. And what was already known what is in fact that the size of this kernel is p to the e minus 1, so it's a p group. And in fact, we prove that it's a cyclic group. So the point p1 f of p is a generator of this group. And now, so I guess I should explain the joke to non-academics. Usually we have reviewer 2 is the one that always kills your paper very badly without mercy. Now that we have a natural question, so isn't it trivial? Isn't it always true that the group at infinity is cyclic? Well, definitely not. So if you take a random ring that you like, finite ring, for example, and you compute the group at infinity, this will not be cyclic. But there are some confusion in this topic because of Silverman, I guess, because Silverman proves in his book that the formal group is in fact isomorphic to the maximal ideal of the ring, but the maximal ideal of the ring as another is not the additive group of the maximal ideal of the ring. So the confusion arises from the fact that the group at infinity needs not to be isomorphic to the maximal ideal, and in fact we have many examples where this is not true. So if you take a random small ring, you may hope this to be true, but if you take a ring with a high nilpotency, so a ring that you need to multiply by itself many times before reaching 0, then this will not be true. Okay, so what we still need to discuss is what happens when instead we have an anomalous curve underlying the curve we are considering. So in this case, two possibilities may arise. So the first case is the standard one, which arises almost always. So almost always an elliptic curve which projects to an anomalous curve is cyclic, but not always. So with probability 1 over p, which is negligible if you consider large primes, but still there, it splits as it was doing in the non-anomalous case. So this is an example. So you can consider two curves that are precisely the same one when you project modulo 13. The first one is what you expect. It has a cyclic group of points, but the second one is the special one, which corresponds to the canonical lift of the curve. And this is in fact generated by one point, which is a honest point in the affine part of the curve, and the point at infinity P1 f of p. So this subgroup you always have, but not always you have the splitting. Actually, almost never in the anomalous case. So if you collect all these results together, then you have this ugly classification that I will not discuss in detail, but it just means you split over your prime powers, every prime power you discuss in the way that we did so far. Okay, so last 5 minutes I will tell you about some consequences. So the kernel of this projection looks an easy group. In fact, it's easy, but it's not trivial. So it's not easy in the sense that you can really predict what's happening there if you take exponents large enough. But it is still easy. So in this paper with Riccardo, who is in the audience, we proved that you can compute scalar multiplication of points at infinity in a way that is not even fast. It's like immediate. So usually you do double ONAD, or you do the algorithm you prefer, and you do like log n operations if you want to compute n times p. In this case, we do 0 point operation. We just evaluate polynomials, and I give you the coefficients of the point that is n times p immediately. So this is a crazy magic that is absolutely scaring from a discrete logarithm perspective, but it is only true for points at infinity, which in the case of fields means it is true on one point, so it's not interesting. But over rings, this is kind of a surprise. So it is also natural to consider the opposite question. So we classified every possible group arising from elliptic curve over z modulo nz. So now if I give you a group, does it arise from a curve over z modulo nz for some n? And the answer is not necessarily. So there are groups that do not arise from any elliptic curve over z modulo nz. This is not surprising, but there are even simple groups, so groups that are not like involved with strange operations. And the problem and the reason behind this obstruction is that the rank of this curve may be very large, maybe much larger than 2, as it was for over finite fields, but it cannot be arbitrarily large. So the fact is that we can bound the rank of an elliptic curve over z modulo nz for any n in terms of p if we want the structure of the curve to be a p group. So if I want to have, for example, an 11 group, so I want you to give me an elliptic curve over the integers that you like, but I want all the points to have order 11. You can do it, but you cannot do it with more than 5 pieces. And the bound is sharp in the sense that, in fact, you can find examples where you do have 5 pieces of this curve. And the last consequences I want to mention is the well-known attack to the anomalous discrete logarithm problem. So it is well known that if you want to construct an elliptic curve discrete logarithm problem, you don't have to pick anomalous curves, because those are kind of the worst candidates that you can find. And in fact, this group structure gives you a way to construct a direct isomorphism from the curve to the base field without involving p-adics or formal groups or formal logarithm or other stuff. So it's something that you can really teach at an undergraduate level. And it only relies on this proposition here. So this proposition says, if you give me a point in the large curve, so the one extending the anomalous, I take this point, I multiply this point by p to the e minus 1. E is strictly required to be at least 2, so it means that it has not to be a field, so we really need the ring structure. I multiply this point for p to the minus 1. I take the x coordinate, I divide it by its y coordinate. This will be a number divisible by p to the e minus 1. I remove the p factors, and this is the homomorphism I create. This homomorphism has a kernel, and the kernel is the same group as before. So the kernel of this homomorphism, is a surjective group homomorphism with the same kernel as pi. So people who loves diagram chasing already knows what I'm going to do. So since they have the same kernel, I can invert pi. So inverting pi is what is usually called lifting a point. There is no canonical way of lifting a point, but the key part is that any lift of the point will work because they have the same kernel. So although this is this specialty is really working only over anomalous curves, because this pi and this theta has the same kernel. So if I want to construct an isomorphism attack from the elliptic curve over Fp to the field Fp, I just lift the point, any lift will work, I apply theta, and I find the constant I like. So this concludes my presentation, and I'm open to welcome your questions, probably offline.
Thank you to everybody, and now it's coffee time. No, wait.
Okay, now wait a second. Elisa can closer. Okay, so before I let you have a coffee, just 2 minutes. So method number 1, Elisa come forward a second. So everybody that comes to the social dinner, if you have special requests like vegetarian menu or whatever, go to Elisa now and she'll take note of it, please. Okay, thanks Elisa. Second method, we're speaking of the CIFRIS as a community, and we emphasize there are cryptographers in Italy, there are cryptographers abroad, and we like to think of ourselves as one community. Well, this is not just chatting, this is not just conferences, but we do also practical stuff. This year we have had a course, an online course, with 10 lectures. The lectures were given by Italian lecturers, some of them in Italy, some of them abroad. It was a huge success. And now there is a small surprise for you. Quindi adesso facciamo una piccola sorpresa. Vediamo se la regia è pronta.
Classical cryptography to modern cryptography. And in modern cryptography, we actually...
instances can be verified in polynomial time, meaning that there is a certificate.
Two things we don't know is R and R. So what we have here is like we have two equations. And
okay, so cryptographic commitments are evidence of
real execution of the protocol between Alice and Benjamin. Okay, so I take this as granted.
I like you and 0 if I don't like you, and then the trust, and then the cryptographic protocol should compute the product of the two.
We will learn the number of elements in the Alice.
By motivating the access control problem, such a problem deals with the special
value, which is based on feedback from other users, and in fact, oftentimes appearing.
There are a lot of cryptographic protocols that are not right.
And now coffee.